শুভঙ্কর স্যার শুনতে পাচ্ছেন? হ্যালো হ্যালো রিজনদা বলছি, তুমি এসছো তো? না, একবার এসো না, আমি এসছি।
हेलो। हम्म। Good morning. The speaker will be joining us within a few minutes and then we will start immediately. Thank you. Good afternoon. Our speaker was in a meeting, so he has concluded it now. So he will be joining us shortly. Kindly have patience and stay with us. Abhijan sir, if you are online, can you do a little audio and video check for us?
Hello, am I audible?
Yes, yes. We can see you also. Mhm.
Thank you.
Can you share your screen once, sir? Just to check. Yes, sir, it is visible. Thank you. Okay, good afternoon to all the participants. Our final day of our 5-day FDB program. The first session is about to begin. Our speaker for this session is Sri ABHIJAN Bhattacharya, who will be delivering his speech on the topic Sustainable 6G through Splitting AI Inference and Semantic Communication. Before he begins, few words about our distinguished speaker. Sri ABHIJAN Bhattacharya is a senior scientist in Network Solution and Services, Tata Consultancy Services. He has done his BSc honors in electronics and BTech in information and technology from University of Calcutta. He completed his Masters of Engineering from Jadavpur University. He has an industry experience of over 21 years. His present areas of interest are enterprise solutions in 5G, networked AI for 6G, 5G core network, signal processing, quantum internet, etc. He plays significant role in national and global technology standardization and belongs to the Indian delegation in World Telecommunication Standards Association. He authored RFC 7967 in the domain of lightweight protocols for IoT, which is the first indigenous contribution from India to IETF Internet Technology Standards. He is a four-time recipient of IETF Next Gen Fellowship. He also actively contributes to 1M2M. He has over 40 granted patents in different geographies around the world, including the US, European Union, China, Japan, Australia, and India. He has several publications in renowned international conference proceedings. We are very happy that such a distinguished personality from the industry has joined our FDP as a speaker. So we won't keep you waiting anymore. I would request Abhijan sir to take over the session. Thank you.
Um, Thank you, sir, and thank you, Techno India Banipur, for inviting me. So, if you may please allow, I can share my screen and start the talk.
Yes, sir, you can begin.
Thank you. Just give me a minute. So I'm sharing my screen. Let me know if it is visible.
Yes, sir, we can see it.
Thank you. Right. So, good afternoon, everyone. What I'm going to talk about is a very nascent as well as very important topic for the 6G and beyond communication. So, but before I go to the topic, to set the context, I want to first start with a video. Oh, just give me a moment. Let me stop sharing and reshare again. There's a problem in playing the video.
Sir, I think you have to turn on the share with audio option so we can hear the audio of the video as well.
Not really, actually, there's a problem in playing the video itself. Let me see.
Okay, okay.
Give me a minute. I'm not sure why it is not running. It should run. Saying that now cannot play the media. Just a minute.
Okay, let me introduce Julio Fugat.
So I'm playing this video off from my PPT. I'm just playing it on my screen. And then I'll switch to the PPT. Okay. Please confirm if you are able to see my screen.
Yes, sir, we can see the screen.
Right. So I'm showing you a video over here. This is usually how I start my talk.
My account director from
Are you able to hear the voice?
whether we have been defining.
Yes, sir, we can hear the
In the
voice.
video?
Potential of
Right.
5G.
So you see this jittery video, right? And you see, actually this was captured by me in my personal mobile phone. I was just standing in the crowd in Valencia in 2019 in Global 5G Forum, one of the inaugural events, right? And I captured this video from a distance, where what you see over there is on the podium. It is basically a stage, and in that stage, two persons are talking live.
Demo that we are seeing today here, please. Yeah. So this real-time holographic call is possible due to the 5G standalone infrastructure deployed in Valencia by Orange SAT. So as you mentioned in your presentation, Thomas, we are covering with standalone the three main. Could you please share with us technical things? Great, amazing. You look smarter than you are, Julio. He's Italian, but believe me, he's smarter. He's smarter than in real life. Well, Julio, let's talk about behind the technical strengths.
So you see, there are two persons talking, and one person is actually not really present on the stage, right? And one person is present on the stage. Now, you have for some time you have seen the video. If I ask, or if I take a poll, so is there any guess like who is the real person and who is the person who is actually not present there? Anybody can make a guess? Just unmute and speak out. Hello, am I audible?
Yes, sir, you're audible.
Yeah, so I'm just asking from the house if anybody can have any guess. I'm saying that there is one person who is not real.
But the
And
person with green color suit, I think, is not real.
any other guess? Anybody has any other opinion? Anybody thinks that it is actually the black one?
No, sir, it is difficult to guess.
Right. So we have heard that the green one is not real. So one idea is that the green one does not have a shadow. As you can see over here, the black one has a shadow, right? So the green one is actually a three-dimension holographic presence of a person who is the director of 5G Vodafone, Orange Telecom in Valencia. And this person is standing 5 kilometers away in a holographic infrastructure. And that image in 3 dimension is being transferred to a 5 kilometer distant auditorium where there's a physical person who is interacting. Okay. This is a situation. And they have a 5G standalone core here. And this demo was in place in 2019, just after, I think, 19 days of launch of 5G in entire Spain. So this is exciting, and this can look like future because so this kind of applications will get rid of the very limitations of existing, video chat kind of applications where you don't see the person really, and you don't get the body cues, which is very important for any communication. There are several non-verbal cues that get exchanged between two persons to convey the, to have many interpretations or inferences to be drawn, or for mind shares, right? There can be many conversations which are not really spoken, but through body cues, and that is why physical presence matters. Now I come to the presentation. So if I tell you there are two persons here on the screen, by the way, how do I get rid of this ribbon from here? I'm not able to get rid of this ribbon. This is annoying. Anyway. No, it's okay. So there are two persons on the screen who might be asking that with all these excitements, what are the challenges do you see? Do you know both of these persons, who they are? I mean, the left one is quite known to...
Recording in progress.
The left one is known to us. And who's the right one? Any idea? Who are these two? At least someone from the house should be able to tell at least the left one.
Jesse Bose.
Left one is Jesse Bose, right?
Yeah. And right one is probably John Marconi.
No.
Probably, not sure.
No. Any guess? Who is the right one? Any idea from anyone? Okay. The left one is Jesse Bose, and the right one is Claude Shannon. Those who might have studied a little bit of digital communication or modern communication may have got one chapter at least where which is based on Shannon's theorem. So why these two people will be asking these questions? First of all, whatever modern communication that we see, the first of its kind, the possibilities were shown in his lab in Calcutta by Dr. Jesse Bose, where he could actuate one device from one building, sitting in one building to another building. I mean, he could, I think, lit gunpowders from sitting in one building by sending commands to another building using wireless communication. And that was of the order of gigahertz, 60 gigahertz probably. And then, since then, wireless communication picked up. And today, whatever frequency JC was used at that time, today we see similar frequencies being talked about as we move to 5G and 6G and beyond, right? And there was one more person, Clark Shannon, who actually formalized the cradle on which modern digital communication systems or any modern communication-centric distributed systems are based on. So, first limitation comes from the limitation of electromagnetic wave, which is driven by the speed of light. How quickly light can travel from one point to another, despite its, and that is the limit that we have. And the other thing is that how far can you increase the capacity of your channel to pump the data? That is the problem of bit rate. All modern communications first design the channel capacity, how much data can be pumped in to the channel. And that theorem comes from Shannon's law. But that also reaches to a limit due to physical limitations, due to limitations of physics. Shannon's law also maybe can predict a limit to which the capacity of a channel can be increased. Now, if we consider the video in this case, there are two persons with one person's hologram going to the other person. This solution is not really scalable, even in modern times, with whatever technological advancements we have. Scalable in the sense, if you consider the geographic boundaries. So right now, suppose I want to do this kind of, deploy this kind of a solution from Calcutta to Delhi. Even then, the latency that it will incur, just because speed of light can travel in 1 millisecond, it can travel only 300 kilometers, not beyond that, right? And you have seen the conversation, how the conversation was going. You cannot really wait beyond a certain milliseconds for the other person to respond. And when this person is present in front of you in 3 dimension, and it is just taking time and responding you back, then this becomes very uncomfortable for the viewers, for the person who are interacting with that ghostly image in front. And it does not satisfy the performance indicator for the users, right? The quality of experience degrades. So both these great men actually predicted how far we can go. Despite all the promises that we are having and all the nice dreams that are being sold, that are being promised, these are physical limitations, both by mathematics and physics. You can't really go beyond that, okay? So Shannon and Weaver, these two scientists, they in 1949, they came up with a seminal work where they tried to formalize the problem of communication. The fundamental problem was technical problem. So you have signals generated at one end or some information generated at one end, then you transfer that information to other end. How accurately you can do that? And that is why if you read in networking books, you have got all these redundancy coding, then error correction mechanisms, ACKs, NACKs, and forward error correction, backward error correction, convolution encoding, and all those sorts, and also source coding, by which you compress the data just to send the meaningful information. So information was the key, and how you encode that information into symbols and you send it to the other end. The other problem was whether the symbols that you have transmitted convey the desired meaning. What do I mean by here? And this is very tricky. What we really communicate is not always the exact things that are there at one point. For example, let's consider this. When you are reading a news report, you are not really visualizing what has really happened, right? Somebody either have directly visualized, or somebody has gotten certain testimonials or certain eyewitnesses who has conveyed some information. From that information, somebody has created a report, someone has edited that report, and then it has been printed verbatim. The edited copy has been printed verbatim, and it has been sent to your home. And then when you read that report as a newspaper, common newspaper reader, while reading that, you also create a visualization in your mind while you are going through. Constant visualization keep on appearing back of your mind, and that gives you the final inference. What is the message of that report? Now, if you are reading the same report, and your friend is reading the same report, back of the mind, the visualization that you may derive, the visualizations that your friend may imagine, these two are not going to be same. But end of the day, in terms of forming the common opinion, what we will find is that the newspaper report, the concerned report, has formed the common opinion amongst whoever has read it. So none of the readers are conveyed the actual scenes, actually what happened. None of the readers are conveyed on specific instructions that how they need to imagine whatever is written in that. Neither the newspaper is sending the exact images or exact video accompanying with that report. It is not possible. So what we are essentially transferring here is a semantics. The newspaper reporter is basically encoding the exact happenings, the exact visualizations into a semantics. And that semantics is further encoded into a different form of media, which is text. It is not video, it is text. And that text is corrected, trying to make foolproof with a dedicated supply chain, that is the channel, to reach the end consumer in the most untampered form, most trusted form. And then the reader is reading that. Reader is decoding the semantics from the textual context. And from that semantics, understanding, getting a visualization. And from that visualization is getting the intended inference that the newspaper reporter wants to convey. This is the entire chain, a typical communication. Here, so the exact information is not, in many cases, of our interest. What we deal with is inference. And that is where semantically correct communication is getting importance. The other thing is, I send semantically correct information. I ensure that the semantics are properly identified, properly understood by both parties. There is an agreement. But then what is the effectiveness? Whether the receiving party is doing the right thing. So I am controlling a robot from here and I'm sending the commands. The commands are same as I intended. The inferences are drawn same as I intended, but the actuation is different. Then that is another problem. So if we look at the entire communication pipeline, there is a technical problem, there is a semantic problem, and there is a effectiveness problem. Whether it, despite all the ordeal in ensuring that the symbols are transmitted correctly, semantics are understood, whether the communication is finally effective. Now, again, I shall have a problem in playing this video. So just bear with me. Let me see if I can get this video from somewhere. Wait a minute. Can play it from here. For some reason, I'm not able to play the videos after presenting. So this is double robot. So this is just a hardware, telepresence hardware that we use to build our own custom
telepresence solution. So telepresence is basically, so as you can see, there's a display and there's a film. So it is basically a multimedia conferencing system on wheel with embodied intelligence, which partially runs on this module and may also be distributed to cloud or the edge computer that may be associated with the wireless network to which it connects, right? So it is a mobile device essentially. And to develop it,
So now in this video, you see there is one person sitting in one laboratory and there is another person watching that person in another laboratory wearing a VR glass. And what this person is watching is not the exact person, but a digital avatar of that person. And that digital avatar is basically mimicking what this person is doing. And although this does not look very good, shabby, because this was just done to create a concept demo. Now this person is standing in, so whatever you see over here is basically what this guy is seeing by wearing this glass. So what this person is doing is basically this image, rather than a holographic image, this is a 3D replica of this. Now this replica can always be as realistic as possible to this person. And then this replica can transmit the voice of that person through here, through this mouth, virtual mouth, and can replicate all the hand gestures, right? So why should we at all go for this? That's a question. Or why did we do this, right? I'll come to that later in detail, but if we look at the semantic problem over here and the technical problem over here, see, from the previous one, from this, in this case, my intention is to interact with the person in full body. And for doing this, the technical problem is huge because it generates terabytes of data. And then that data you need to send across several hundreds of miles or thousands of miles. You need an intermediate infrastructure over the network. And that network has to bear with the sheer volume of data. And it is not only one user, one pair of users using this service. This has to be a service which is democratically used by many users. The kind of load it will have on the network is immense. On the contrary, the demo that I showed you, this one, right?
just a hardware, telepresence hardware.
In this case, what we are doing, this person is standing in front of a camera, normal RGB camera. There is a local intelligence who is inferring or predicting the body gestures. Just getting that amount of data, sending it, merging it with audio, and sending it across to a receiver where a replica of this person was a one-time replica of this person was already put there. And this person, whatever the body gesture is there is being put on that replica. Rather than sending the exact video, I know that from that scene, what is important is this person. I get that person out from the screen, from that scene. I mean, here the intelligence. And then that intelligence is encoded into a semantic information, which for per frame, that information is just on the order less than a kilobyte. So what used to require per frame almost terabyte of information is now reducing to kilobyte of information, and then you can send it across. Okay, it sounds very fancy, but now the challenge comes. Because this is, we have implemented this. Whatever I showed you is the intention. It is not the what is happening at real time, because there are a lot of challenges. And it's a very, very interesting research paradigm that everybody can invest. So today, AI is everywhere, and with 6G, AI and communication, it started from 5G. We're talking about an AI native network. There are two things. One is AI for the network to make the network more intelligent, more resilient. You put AI, and also make the network prepared such that deploying any kind of AI algorithm as an integral part of the solution becomes easy. That is called AI for network. So two things. One is AI network for AI. The other thing is AI for network. Okay. Combinedly, if these are natively supported, so whenever I am getting the network, I know, or whenever as an application developer, I am developing an application which needs a lot of intelligence that needs to be offloaded to somewhere, or I need some computing powerhouse where this computation has to be done, the AI has to be done, it will automatically can be offloaded. I don't have to worry about installing a new infrastructure. The same way, cloud is already here, but it is not same as having cloud. Okay, why? I'll come to this later. Now, why we're talking about AI in this case is because if I go back to this example, if I have to make it a very democratizable solution, right? So, yeah. If I have to make it a very democratizable solution, this terminal is not going to have much of intelligence. I mean, much of computing power. This may be your smartphone or any small, any ordinary laptop without any high-end GPU or computing power. But when I say semantic identification has to be done, this normal communication chain does not allow you to do that. You need some AI at the application endpoint who will detect this entire scene, will identify what is the, will identify the body of the person, and then will also identify the body structure, the instantaneous change in the body pose that will get translated over here. And these are very, very complex and very computation intensive algorithms, which cannot run over here. So semantic communication may sound very fancy, but the challenge is doing the semantics, I mean, getting the semantics out from the actual information is very challenging. And also, the exact scheme is driven by task. Having said that, so you see, there is a mobile tower and there is a computing infrastructure. Essentially, we call it mobile edge computing, or in most approved terminology, it is called multi-access edge computing. Now we go back here. So now you'll appreciate why now computation and communication evolution, the generations, are now going hand in hand. Because the future communication, as we see, the 6G vision, the kind of control, the kind of experience, the kind of coverage, etc., is being talked about. It is not possible without having artificial intelligence at the core. So communication only dealing with transferring of symbols is not just enough. Artificial intelligence for network and network for artificial intelligence has to go hand in hand. Now, there is also a talk about sustainability, and we will come to that. So as we said, we talk about society 5.0 and whatnot. Everywhere at the top of the knowledge pyramid or at the core of the pyramid there has to be an an acquisition of data, analysis of data, inference, automatic inference from that analysis, and also, wherever applicable, automatic actuation. But the question is, where will this AI sit? Will it sit at the end terminal? No, because this huge computation, and you have to also consider the training required. The end terminal is not going to give you that space, that capacity. Is it entirely going to have in edge? Then you can have. If you have to, as an implementer, if you have to ensure that you always deploy the edge to have your computation, to have your application running, this becomes an overhead, infrastructure overhead. Also, edge does not have full capacity as cloud. Now, if you put it on cloud, you have endless computing capacity if you have the money to pay for it. But at the same time, you succumb to high latency. And this is not acceptable for many real-time use cases, as I showed you, highly critical real-time use cases. So that is why the telecom operators and computation service providers have combined, and the computing service is being integrated more and more with the network infrastructure, so that the application developers and the end consumers alike, the enterprise users, they don't have to bother about this computation overhead, or they have to worry at their end about keeping this infrastructure at their end. This can be part of the application offering itself, but the application provider may ensure that at the site of deployment, the deployment already gets an edge service from the operator who is serving the network. And there can be several price models, business models, etc. We are not going into that today. Now, why we talk about sustainability. You see, what do we mean by sustainability? First of all, when we say technology is sustainable, there are many things. First of all, green energy, the carbon emission has to be reduced. It has to be recyclable. It has to be cheap. There has to be, it has to be eco-friendly, etc. Now, why we talk about 6G sustainability? What are the big concerns? You see, if you do, I mean, let us go back to that 3D communication. In that 3D communication, if you pump that much data through the network, you can understand how much energy the communication pipeline has to consume. At the same time, you can imagine how much heat it is going to generate, the communication pipeline itself. Fine. So we talked about semantic communication. In semantic communication, I'm trying to concise the discussion to semantic communication for today. When you talk about semantic communication, you can say that by semantic communication, we are reducing the carbon footprint because we are not sending enough bytes. We're just sending, you said, you just need kilobytes of data to be sent. So that's good enough. By sending kilobytes of data, I'm getting the effect of terabytes because I'm getting the 3D interaction. So we are done. We have met the sustainability goal, but that is not quite true because if you look at this picture, who does this computation and how much load this computation is going to take? Even if you are not doing it here, you're doing it in the cloud. Just imagine how much heat the data centers will keep on generating, because tomorrow the data centers are not going to be just data centers. They are going to be neural network centers. You may not have, as we said, semantic communication is a task-oriented communication. You may not have all the algorithms installed in edge or in end terminal. All the neural network models you may not have, depending on the task. You may be doing several tasks. So even for semantic communication, in this kind of scenario, this needs human-centric model, prediction model. If you just forget about this human, if it needs to draw just a scene graph to a much detail and generate captions, then your model changes. Because these models are also task specific. There is a single AI model that does all. No. Again, you need there may be some use cases where you need to do some intelligence on audio. How you are going to do that? You will need another model. How many models can you store? So the neural networks are going to be in the cloud. You may fetch the neural network, or you may commission the neural networks in the cloud itself and ask them to give you the result. Now, again, as I said, putting it in the cloud and entirely relying on cloud will not give you the interactive experience. You can put on the edge. Edge also has its limitations. How you're going to handle that? Anyway, let us say we are doing it on the edge, or we are doing it in the cloud. Irrespective of whether we are doing it on the edge and we are doing it on the cloud, it is not, again, a single user who is requesting for a service and being served. Millions of users. And for the edge computer, there may be hundreds of users coming together. For a cloud, millions of users coming together. And these algorithms, these high computation intensive algorithms will be running in the data centers or the edge installations for numerous users, right? And what they will do? They will consume power. So while you are freeing up the communication pipeline, but you are actually blocking one communication. So first of all, the entire video and everything stuff are to be transmitted to the neural network. Before that neural network can start working, the input has to go there. So anyway, you are sending all your video data, all that high bandwidth data to either the cloud or the edge, right? And these guys are again starting to compute this high-end computation, and this is happening for n numbers of users. While you are freeing up the back end over here, maybe. But what are you doing here? You are just dumping more concerns on regarding carbon emissions and regarding warming and regarding data consumption. So one approach, now we have to do this AI, right? Now I'm coming to another topic which is merged to it, the splitting of AI, okay? One approach is that, so if I have a neural network, in terms of both energy consumption and in terms of latency, like how quickly I can get the data, the idea that is coming is this neural network, see wherever this network can be split. So this is not a distributed computer. No neural network is really designed keeping in mind distributed computing paradigm. Neural network is conceived as a monolithic thing. But the way the neural networks are created, there are layers and there are connectors. So from one layer to one connector, you have certain connections. I am currently only considering the feed-forward network. I am not considering any recursive neural network or anything, okay? So from one point to another point, you are feeding the data, and every layer is consuming, for simplicity, every layer is consuming the outcome of the previous layer, the intermediate data. Now, what if we split depending on the current condition? So the problem is for the end devices, it has to store and compute this entire network. If I have, say, 50 layers or say 20 layers, I have to compute all the 20 layers if I have to execute. There may be, I mean, I'm not considering this network compression, because these are network compressions are happening for dedicated purposes with agreed reduction in accuracy. So I'm not considering a neural network compression. That is not a scalable solution. So if we have the data, if we have the network, if we split that network, what is the effect? First thing is, the end device need not send the entire input to the network server or the cloud, okay, whatever it is. So that way, I'm saving the communication pipeline, this pipeline that I'm talking, this pipeline. So I'm not sending this or this, okay? I'm not sending the video to the intelligence center for inference. What I'm doing is, at the end terminal, neither I am computing the entire computation here. But I'm stopping the video over here. I'm not letting the video to go over here. Why? Because I let the maximum of the neural networks to be computed there, but I compute only this few. And this will not actually take much of the GPUs, these two. This is a small part. I'm not doing the whole computation. So I'm stopping the network to flow, the actual, this, say this is a 8K video or at least this will be of the order of megabytes, 1 or 2 MB. And for large cases, this will be of the order of 8K or 4K. So I'm not sending that. I'm freeing the pipeline. At the same time, I'm just doing a little bit of computation over here. And all this intermediate data is usually of the order of kilobytes. And this intermediate data I'm sending over here. We have done some profilings. If I have, I'll show you. Now, fine, that is fine. So I'm doing the benefit of, removing the, this actually helps us in getting the latency benefit. And also this helps us in saving the bandwidth. But then we're also claiming that this can also help in sustainability. You'll ask why. So I'll just request you to appreciate this. So on the left side, there is a large big image of a large forest fire, right? Across region, okay? There's a huge forest fire. And this will have environmental effects. This will have environmental, global warming effects and all. On the other hand, just imagine winter is coming. Entire north hemisphere, most of the area will be, there will be winter. And suppose we are in a much more medieval age and we all soak our hands in fire. Now, if you collect this small fire pockets in the entire north hemisphere at different corners, will it be, if you look at the volume of the total area that fire is lit, and if you just add up or sum the temperature that is being generated, probably you will see that mathematically you are coming to a figure which is much more higher than what would have happened in a jungle. But if you look at the environmental impact, such distributed small pockets of fire and that large fire does not have the same effect. Such small distributed pockets will dissipate the heat and the carbon emission within its vicinity. So there is a distributed dissipation of energy or distributed dissipation of the heat that is generated, and also the kind of fuel they will require, right? Now try to appreciate it from that perspective. Rather than sending or allowing the cloud to do this, to do computation for all or pushing everything to the edge, what if we distribute the computation? Then what we are doing essentially, the UAs or the user equipments are taking, because the user equipments are also, improving in their capacity. So the user equipments are improving the heat dissipation requirements and also the computation load that is associated with it. So from this respect, we can think about a situation which can come in future. So a mobile phone, I'm sorry, I mean, this is not visible. Let me, so a mobile phone can actually, distribute the load for computing. So certain layers of the neural network can happen in a nearby phone, which acts as an edge. Certain layers of the computation happens at the EV, which does not have enough energy. And certain layers of the computation can happen over here, depending on how much you can split. Okay. And this is also important that not every layer can be, split. And not every layer can be, you cannot split it from every layer. It depends on the exact architecture. So this is what kind of a profile we did on YOLO version 5 for sending a 2 MB image, and then you just split it at this layer. Okay. You see, the input image is 2 MB, but when you look at the first layer, just after the input layer, when you look at the size requirements here, right? The size requirement is in KB. So just after the first layer, an MB image, after the first layer, I just need to send only, say, 15 KB of data to the next layers. So that helps. And also, if you look at the computation, so in YOLO 5, what we have seen, only up to 4th layer, we can, because of the recursive nature, only we can, up to 4th layer, we can split. So if you look at the total G-flop computation graph, and this is where the problem is, because a terminal will need to compute this entire, although YOLO is still on a lighter side. I mean, a lightweight, much more. You can run in your terminal with a reduced performance. You need a higher time budget. But if you look here, this is only this much computation you need to do. And for this, your processor may allow you jolly well that yes, we can do this much. And send the intermediate data. Send the intermediate data. So we have done certain experiments where we could see that the benefits are there. Now, this idea of splitting emerged from about 2016, 17. Many papers were done. But this was mostly in the view of cloud computing, considering that there is one terminal, N terminal, and there is cloud. So the N terminal splits a little bit of data to the cloud. But now with 6G, we see some of the researchers have come up with a rejuvenated interest, because now we are talking about not just cloud, but we're talking about edge control as well, right? Because cloud, the more you go to the cloud, the more you have the delay. And so local decisions need to be offloaded to a local edge. So now the splitting will also happen in a tripartite fashion. So there is cloud, there's edge, there's a interval. In a triangle, you can consider that this AI inference splitting, so not all will be split between the robot and the cloud. Not all will be split between the robot and the edge only. In some cases, it may be split between, I mean, robot means in this case, N terminal, the N terminal and the edge. In some cases, it may be between edge and the cloud. Some cases, all three may be involved. So we consider that this is one step towards sustainability and towards, while ensuring that there's a good performance, but still you get the good, it is a multiple optimization possibility that we see with this kind of approach if we combine semantic communication with this kind of splitting techniques. And I don't know whether this video will play. Yeah, this video is playing. So this is what we did in our lab. So I think last year, what we demonstrated. Now this is reality, what it happens. So we were just sending the data. We were and you can see the latency that it has. About 4 or 3 seconds of latency we have from copying one gesture to the other, while the data was being transferred over, routed over a server in Mumbai. And what we found is that most of the communication, most of this was happening due to computation, the algorithm. Okay, most of this was happening due to this algorithm, right? So with this, I would like to end the conversation. Okay, and let me show if this demo works. Is it working? No, this video is off. Anyway, let's forget it. So with this, I end the discussion. And this is what I was saying, like the YOLO version 5, you see, the version 5 of YOLO, it is quite old, but still for simplicity, we took it. You see, only these 4 layers are, feed forward, but all rest of the layers are recursive. Now you can't, so this is, I mean, if anybody has any interest in, graph partitioning, and they can get involved in this kind of, I mean, they can steer their work towards this kind of use cases. And this is where you see, this is a typical graph partitioning problem. I mean, how do you make this graph bipartite? I mean, the most obvious thing is here, right? So this is also a food for thought for those who are involved in AI model creation, right? So they may also think of, restructuring the models so that there can be hooks can be created easily to, to make that network, I mean, to split that network in a bipartite form so that adaptively at selective points, the network can be divided into head and tail segments. As here, one head segment that goes to that receives the input, okay, that goes to the N terminal, and the tail segment goes to the back-end computation, right? So these are some research ideas that can spawn from here as well. So, okay, thank you. If there are any questions, I'll be happy to take.
Thank you, ABHIJAN sir. The participants, if you have any question, you can ask to sir, or you can type it in the chat box. You can unmute your mics and ask your question directly, or you can type your questions.
So
We'll
if there are
just
no
wait for
questions
him.
right now, you can drop me. If you have any questions, you can drop me over. My number is there with the organizers. My email ID numbers are there. You can simply connect me over that, and
Okay, so sir is saying you can communicate with him directly through
I see.
email. You can collect it from the organizers, from our conveners. So if there are no questions, we won't keep sir waiting. Sir, thank you very much for your presentation.
Thank you. So I'm then leaving the meeting. Okay.
Okay, sir. Have a
Okay.
nice day.
Bye.
Recording stopped.
We will resume at 2 with our second and final session of the FDP. See you participants. We will open the link at 1:50.
Recording in progress.
Because these companies are also producing ample sensors, and that's why lots of wearable devices are coming. Along with the smartphone, there are tablets, drones, everything is coming. Beyond 2023, that will be an era of actuating. So then the driverless car, we are talking about driverless car, space travel, telemedicine, doctorless operation, or teleoperation. A doctor can do the operation from far end. All these things can be possible 2030 onwards. So, what is there in the fourth and fifth generation sensors? This is the block diagram of fourth and fifth generation sensors. You can see the sensing element is MEMS, that is micro electromechanical systems. And in fifth generation system, instead of a single sensing device, a sensor can sense multiple physical parameters. So multiple MEMS are embedded in the fifth generation sensors. Now the question is, why we are talking about MEMS? This is the full form of MEMS, that is micro, M for micro, E for electro, M for mechanical, and S for system. It is a system as it is a combination of electrical and mechanical components together on a chip to produce a particular system that is in miniature dimension. So what is the use of this? First of it is having better sensitivity. Number two, due to small size, we can easily carry it out. So it is very easy for carrying. Then other thing like it will take less space for installation. No mechanical hysteresis will happen because of the small mass. Then cost effective because we can do it in batch processing. So for a particular fabrication, we can produce millions of sensors together. So cost will be minimized. And the most important thing is it is easily merged with VLSI technology, and it is silicon based. So sensor and the associated circuitry we can produce on a single chip. So after fabrication of such a device, we can call it as system on a chip or lab on a chip, like that. There are three pillars in MEMS. First one is the design. Design is very, very important. Physics, that is the physics behind it, and the working principle of the device. That depends upon the physics. And the design also matters that which way we are going to produce it. Like mobile phone, that is rectangular. The PC, laptop we are using, that is also rectangular. The water bottle we are using, that is circular. So when we are making the sensors, it should be, whether it should be rectangular or square or circular or oval or pentagon or trapezoidal, all these things comes from the engineering knowledge or design. That is also we have to take care. Okay. Then second one is the material, because characteristics of the device depends upon the material. That's why when we are purchasing any dress, we are very much careful about the material. Third one is the fabrication procedure, because there is a huge difference between micro and macro devices. Macro devices we can see through our eyes and we can do it. But in micro level, we can't see with our normal eyes. So it is quite difficult, and you can understand it is on silicon. So there are some rules and boundaries that we can have to follow. And the thing we are doing in macro that cannot be possible in micro. So fabrication is a challenge on research area here. So these are the steps of fabrication. I think everybody will be not interested, so I'm skipping it. Now we can see the applications in different sectors. First one, smart sensors at our home. We all have actually heard about smart cookery, that is oven, smart oven, coffee tea maker, washing machines, vacuum cleaners, smart cooking. This is here you can see, you can do the recipe and it will prepare. Then other, that all these things in the smart kitchen can be connected with your mobile phone and we can start it automatically. Food, drinker will be ready when you are back from office like that. Here you can see motion sensor is there in the dustbin. So when someone is coming, its lid is opening. Water, water sensor to prevent leakage or damage in washing machine. Then this is glass break detector sensor. Sometimes we are worried about glass breaking in the windows or doors. This is plug-in gas leakage sensor that we can use in our kitchen so that any abnormality happens, there is an alarm. So this is in a semi-automatic car. Here you can see how many smart sensors are connected for tire pressure monitoring, for pressure and inertial sensors, for braking control, force sensors, mass and airflow sensor, fuel pressure sensor. All these sensors are connected here. There is a crash sensor in front of the car. So when there is an accident, this is the crash sensor that is connected here. So when there is an impact, it will actually inflator, gives a hit, and this impact triggers the airbag that is connected with our steering wheel. So this will come out and save the driver who is driving the car. So there is a smart sensor in front of the car for passenger safety. Now we will move to healthcare. Smart sensor in healthcare. Why healthcare? Because our body is filled with microtubule veins and arteries. These are all micro in nature. So these micro sensors are very effective for our healthcare purpose. So why MEMS are in medical application? First one, as its size is small, so it will intake small volume of reagents such as blood or serum. And due to small size, power consumption is small, so battery longevity will be higher, less invasive, that's why less painful. Integration with CMOS or VLSI permits a large number of systems can be fabricated on a single chip. So system on a chip, SoC, and lab on a chip, LOC can be possible. And through batch processing, we can produce millions of sensors at a time in a single fabrication that lowers the cost of the sensor. And silicon, normally we are used for MEMS devices that is less impact in human tissue, biocompatible one short of that we can use it. So here you can see the sphygmomanometer, that is the conventional blood pressure monitoring device. And here the same device, but it is on our fingertip. We know injection. From our childhood, we are taking injection, needle is required. So with time, needles are becoming micro and micro so that the size is limiting. So the pain that we are feeling due to injection is degrading day by day. This is a common endoscopic instrument. I don't know whether you know about endoscopy or not. It is a diagnostic procedure which involves actually inserting a flexible device from our mouth. Fiber optic is there that is used to take, and camera is also there, that we will go to our internal part of our body to mouth and trachea and take pictures from the internal part of the body. But it is actually a very costly and expensive procedure. We have to visit a diagnostic center for 4 to 5 hours. We have to take some sedative, and after having this endoscopy, there is some one shot of this patient can feel some problems while having food. So there is a solution. Now there is MEMS endoscopy, that is called lab on a pill. The same thing is done by a single capsule size of lab on a pill thing. So here the different parts of the capsule, that is, there is a acid transmitter, there is a optical dome, lens, antenna. So it can take the photography when we are putting it inside our body. And due to small size, there is no problem because our internal parts are
Hello.
red always. There is, hello? Hello? Am I audible? Hello?
Yes, ma'am, you are audible.
Okay. So when we are having this, it can easily go pass through our body parts, because our body internal parts, especially intestine and all, are not even very straightforward. There are lots of zigzag path is there. So when we are going for normal endoscopy, optical fiber is using. Optical fiber has certain bending angle, so it is quite painful. And all the intestine part it can't go through. So for colon checking or all these things, this type of capsule endoscopy is very, very effective. Yeah, hence the example of smart pill. Those people, those who are taking the patient of diabetic, they are having injection every day, insulin injection. So instead of that, if we put smart pill inside our body, this pill is having one sensor that can monitor the body glucose, and there is a reservoir which is filled with insulin. So when there is a down in glucose level, insulin will burst out from the reservoir and it will give insulin as long as the glucose level comes to the normal. And when this reservoir of insulin is empty, then through antenna, there is a communication coming at outside that refilling of the insulin reservoir is required. Another very important smart sensor is smart dust or MEMS dust. Why are you calling it as dust? Because it is so small that it can easily float in the air around us. See the size of MEMS dust on fingertip. So actually the structure is like this. It is having parachute antenna with actuators, power is required, some electronic interfacing circuit is required. Detector depends upon which type of sensor sensing you are willing to do. And mass is only 12 mg. Speed is 10 meters per hour. Energy is only 16 joule. If it's illusory it is 1 milliwatt. So you can understand that this is very small mass can easily float on the air. Here you can see this is the MEMS dust compared with the Dandelion sheet, and here it is in the fingertip. So this consists of sensors, computing circuit, bidirectional wireless communication systems, and power supply. All are integrated in a tiny dust size device that is called smart dust. So if we put smart dust where we can't go, we can put this type of smart dust. We can make a spray, and which type of physical parameter we are willing to detect, that we can do. That we can put our desired sensor on it, and we can catch the data from a far end. So these are the different parts of smart dust. passive transmitter, active transmitter, receiver with photodetector and sensors according to our requirement. We can put it. There is a solar cell that will work at the daytime and battery that will work at the night time. Now, medical prosthesis. As I told you, not only the transducers, these actuators are also called sensors in micro level. So in medical domain, especially in robotic or microsurgery or laparoscopic surgery, which type of medical equipments we are using? When you are going for laparoscopic surgery, I think you may, the question may come to your mind that there are small apertures of few millimeters. How come all medical surgical tools are injected inside our body through that small aperture? Here you can see the surgical instrument like tissue spreader, stents, angioplasty, coronary probe, brain spatula, endoscopy, as I told you, miniature zoom device, bending actuator. Then smart screen are very important for wind turbulence reduction purpose. Here you can see this is for angioplasty. This is the stent. When we are putting inside our blocked artery is blocked. So when we are putting here, you can see it is like a matchstick. And after putting it, it regains its original shape of a netted cylinder. So this material itself works as an actuator. This material is called shape memory alloy. It is an alloy that is solid to solid phase of alloy, two metals, that can regain its original shape. That's why it's called shape memory alloy. And most of the places where we are doing microsurgery or robotic surgery, this type of actuators are using. Here you can see this type of SMA material used in the aircraft here, so that it can reduce the wind turbulence. These are the other applications like brain, in our spinal cord. If there is any bending, we can put shape memory alloy. Then in the teeth, here you can see this is a very interesting application of smart sensor. When we are embedded it in our contact lens, it can measure blood glucose of our body from our teardrops. But it is a continuous process. Those who are using lens, contact lens, they can use this type of sensors. The sensor is embedded on your contact lens so that it can detect the body glucose in terms of through your tears. And then there is an antenna type of thing through which the data goes to the doctor's computer or in your mobile, wherever you are willing to get. SAW sensor. Another very important type of smart sensor is SAW sensor. The full form of SAW is Surface Acoustic Wave Sensor. The beauty of this sensor is that it is not only work as a sensor, it can measure pressure, it can work as a chemical sensor, it can work as a biomedical sensor, it can work as a bandpass filter in mobile communication. So that's why I told that it has its own beauty. It has multiple applications, but here I am showing how it was used to measure COVID during our this COVID time. So there are two interdigited sensors and there is a piezoelectric material in between. So when one gathers the information, piezoelectric material as it is used in our wristwatch, you know, if we apply electrical input, it will produce mechanical vibration. That is in our mobile, in our wristwatch. We have a linear battery and that's why there is a mechanical movement of the pointer. And vice versa, means if we give mechanical signal, then it will produce electrical output. Here, in this type of SAW sensor, here we are giving electrical input. So this tip of the interdigited sensors started vibrating, and the vibration passes to the piezoelectric material, and the interdigited sensor, that is in the output, it catches this vibration and produces the vibration into electrical signal. In between these two interdigited sensors, we are putting antibodies. So when the COVID antigen is present here, that will be catched by the antibody, and we can easily detect whether COVID is present or not from our swab or our. So this is the final look of the sensor. In some countries like Germany, people use this type of ball SAW sensor. Means SAW sensor looks like a ball. The electrodes are embedded on the upper side of the ball, and they put it in the air so that if somebody having COVID, that can be easily detected by this type of sensors. Then for retinal prosthesis, artificial eye, hence artificial eye is also people are trying to develop. These are few challenges, but most probably have been overcome. Then finally, I am going to show you few research work in my lab that was on MEMS-based smart sensors. So first one that I'm going to show you, that is respiration rate monitoring sensor. During COVID, it was very much essential to measure our respiration rate. Normally, a adult person in rest condition, the respiration rate would be 12 to 16 breaths per minute. And the diagnostic method that through which we can measure respiration rate by visual observation, that chest is coming down or coming up or down like that, impedance pneumography, and acoustic sensing. This is impedance pneumography. But the problem is that all these things are spirometric test, all these give you the respiration rate at a particular instant of time. So we have tried to develop a sensor that can measure our respiration continuously, and we can easily measure it in our home. So we have developed array of MEMS sensor that can be connected through a mask and in a way so that it can get the breathing pressure from our without pressure from our nostril. So this is the square type of sensor that we have developed. This is capacitive type sensor. And finally, these are the characteristics of the sensor. Next job that we have done, that is heart rate or pulse rate sensor. Normally, the heart rate is 72. This respiratory abnormal condition, if it is more than less than 60 or more than 100, like that happens. So heart rate is again a very vital sound for a vital sign of human being, whether a person is alive or not. Normally, we are measuring our heartbeat from our radial artery, and there are two types of method we are using. One is touch thing, everybody can do this. And second one is optical plethysmograph. If you remember, when we are going to hospital or any time, they're putting it like this, the optical sensor is there. But problem is that while we are putting it, we can't use that hand. And there are two sensors. One is light sensor, another is light emitter. So both the sensors, you have to give power. So we want to make it energy efficient. Instead of two sensors, we are using array of pressure sensors. These are the 8 places of human body from where we can measure the respiration rate or breath rate. We have used here radial artery thing, and the array of sensors we have produced like this, and it can be easily placed on your radial artery like a patch and can measure your breathing rate or respiration rate. Third one that we have developed, that is MEMS microphone sensor for low power hearing aid. Mostly the persons who are using hearing aid are suffering from the problem of using very costly battery. Battery longevity of this hearing aid is 1 to 1.5 months if you are using 8 to 9 hours per day. So it is quite difficult for poor people to use, to afford the batteries. So there is a pair of microphones that is used in hearing aid. This is the different parts of a hearing aid. So these two microphones we have replaced with MEMS microphone so that it will be energy efficient, battery longevity will be higher. So we have developed the microphones in MEMS, we have fabricated it. This is the circuitry. And this is the performance analysis. Third one, fourth one that we have developed, that is non-clinical detection of malignancy by using MEMS capacitive sensor. Hence, we are trying to develop one lab on a system chip like this, through which one can detect blood malignancy. It should be small in size, portable, so no pathological system is required, and this is lab on a chip, as you can see. So we will give a 1 drop, micro drop of blood. If it is of the cells present in that micro drop of blood all are malignant, then the display will be red. If all are normal, then the display will be green. If few cells are normal and few cells are malignant, then it will be orange. So for detection purpose in block level hospital, doctor can use this. So here you can see to a micro drop of blood, there is a change in impedance. So this portion, if it comes in this portion, means all are malignant. If few cells are normal and few cells are malignant, then it will come in this. If all cells are normal, then it comes into this. So normally for cancer or malignancy detection, we are doing biopsy. In biopsy, it is a human intervention is there. Through microscope, human is intervening whether there is any change in the shape and size of the cell, mainly WBC in this case. If there is a change in thickness or diameter like this, but in our case, from dielectric permittivity or conductivity or impedance change of the cell, we can easily detect whether any malignancy happened or not. So main advantage is that significant changes can be detected in the initial stage. But in case of biological parameter, when a human is looking after, then the main drawback is that significant changes can be detected after a certain period of time because human eyes are detecting this. We have a MOU with this semiconductor lab, ISRO, Government of India, from where we have developed this sensor. There is an in-house facility for fabrication with Intelligence USA, and we have a national collaboration with IISc Bangalore. Finally, through ISRO lab, we have developed this sensor. Here in this small rectangular white portion, there are 100 sensors, array of sensors, and see the size. And it is connected now with IoT cloud. with a micro drop of blood. This type of curve is coming. With TCA, we have tested it with a PHA cell line. PHA cell line is a normal cell line, and THP cell line is a malignant cell line for leukemia. When we are looking for testing in block level hospitals, doctors suggested us to make a device for CBC count. CBC count means complete blood cell count. Normally, people of villages, they have to visit nearby city or town for a simple complete blood cell count, because that type of diagnostic center is not available in the villages or small towns like that. So we have developed one microfluidic device for sorting and counting of blood cell, that is RBC, WBC, and platelet. So this device is based upon the technique called dielectrophoresis. In dielectrophoresis, as you know, WBC, RBC, and platelet are having different dimensions. So when they are passing through, as you see here, positive and negative electrodes, we are applying here positive and negative electrodes. If you see here in the simulation software, these cells actually follows different paths. So we can easily collect them and can count them. So the technique we have adapted here. So main objective of this work, we are willing to make a very small portable test kit, and first detection of anemia, malaria, leukemia, etc. can happen. It should be portable, so anybody can carry it easily, affordable. And so block level hospitals where budget is a limit, they can also afford it, and no prerequisite knowledge is required to use it. So anybody who is coming can easily use it. This is the hematology analyzer that is using in the diagnostic center. See the size. W is required and costly also. So it is diagnostic center is having this type of hematology analyzer for CBC count. And here you can see through CBC count, doctor can predict different types of diseases. So when a person is having fever for a prolonged period, doctor suggests for CBC count and all. Here you can see the simulation. Blood sample is coming, and through dielectrophoresis, different positive and negative electrode passing. And the bigger one is the WBC, middle one is the RBC, and smallest one are the platelets. And everywhere there is counter is connected, so one by one cell is counting. This is the process. Finally, we have developed this. It is 1.5 centimeter for 1.5 centimeter device. We have developed it. It requires low voltage, 3 to 5 volt is required. Battery can be also used for this, and small amount of blood sample is required. This is the device. And Rajaramana Center for Advanced Technology, that called RRCAT, that is in Indore. They have actually helped us to develop this. Their lab, the X-ray lithography lab we have used to make these microfluidic channels on silicon wafer. We have done this. Then COVID era came. So it was difficult for us to visit IISc or ISRO lab or Indore. So instead of silicon, we have started using paper. And this is the same sensor, interdigited sensor that we have fabricated on filter paper. And through this, we are putting on in our mask to measure how respiration rate or respiration of a person affects while they are wearing a mask. or suppose how a person having bronchitis and prolonged bronchitis gives asthma, which way it will affect the deteriorate the performance of respiration. So respiration pattern also we have collected from this. Here you can see the respiration pattern. And now also my students has developed different types of pressure sensor for switching purpose, for flex sensors. So lots of pressure sensors we are working now. Finally, I want to show you some low-cost prototype or proof of concept devices, wearable devices that we have developed in our lab by the help of all these sensors that I have described till now. The first one that I'm going to show you is electrical impedance tomography. Now the question is, what is electrical impedance tomography? You all know CT scan. CT scan means C for computed, T for tomography. What is tomography? And what is the difference between X-ray and tomography? X-ray is a two-dimensional thing and tomography is a three-dimensional thing. If we are having tumor or polyp or anything like that, then X-ray can detect that there is something. But through tomography, it can be found that it is a three-dimensional imaging. So the shape and size of the tumor or polyp, whatever, or stone that can be detected. In computed tomography, there is some hazards for human body because lots of X-ray sources are using. That's why doctor always suggests that there must be 6 months gap between two consecutive CT scans. So this is an alternative of CT scan. This is not at all harmful and it is easy to use, cost effective that we have developed by electrical impedance. So this is electrical impedance tomography as in the definition. It is an imaging technique through which the internal resistivity distribution is constructed based upon the measured voltage on the surface object. Here you can see we have developed a sensory system through which the image, same imaging, this is the lungs function imaging, is coming just like it happens in case of CT scan. So we have used for the first for monitoring the lung fluid movement and for estimation of lung area. It was very much essential during COVID era. Again, we have used this electrical impedance tomography for erythropoiesis, for detection of erythropoiesis. Second one, that is again very effective, that is low cost smart CPAP device. CPAP is continuous positive airway respirator. This CPAP is used, sometimes it is one sort of mechanical ventilator we can use that can be used in the bedside. In home, people can use CPAP. Those who are suffering from COPD diseases, some people are using CPAP regularly at night. If there is any problem of respiration, then we can use this. If, as I told you already, if our breathing rate is between 12 to 24, this is called normal. If it is greater than 24, then abnormality start, it is called tachypnea. And if it is less than 12, it is called bradypnea. In both cases, it is related to COPD diseases. So we are trying to develop a respirator. Respirator is the device for assisting breathing for a long time and helps for long-term artificial respiration. So this is the block diagram. Here we have used a three-phase BLDC motor. BLDC means brushless DC motor. So what is the difference between the normal motor that is running on our head and this motor? Normal motor is brass motor. Brass is used as a communicator. Commutator. Brass is used as a commutator in this type of motor, in the normal motor. But in brassless DC motor, brass is not used. Instead of brass, here we are using some electronic circuitry to control the motor, for driving the motor, to control the motor drive. So commutation part is done by electronically by using some electronic circuitry. That's why size of the motor is very small compared to normal motor, and it can RPM is very high, mass is less. So lots of advantages are there. So normally all medical devices are using this type of brassless DC motor instead of normal motor. So there is a blower, the mask and the respiration rate measuring sensor already I have shown you. So it was connected with the mask and it continuously measure the respiration rate. If there is any abnormality, then it gives signal to the main controller, and if the abnormality consists for 2 minutes or 5 minutes, then it switch on the BLDC motor, which will drive a suction pump that will take air from outside and force it inside our body through our mouth and nostril. So real-time implementation, here I am showing, we are having a patent on it, and this is the thrown away things. You can easily identify this was I got it from a out of order computer hard drive, and these are 200 or 300 cost IC chips, few capacitance and all this, switches and all this. And finally, we made the device and we started testing. So this is the proposed algorithm as I described you. So it is a self-calibratory type of instrument. Self-calibrating type of instrument means it can, when we are using it, it can easily identify our age. As we can see that with time, our respiration pattern varies. Before 50, this is our normal respiration, normal breathing pattern, and this is abnormal breathing pattern. And between 3 to 12, this is our normal breathing pattern, this is abnormal breathing pattern. Between 12 to 50, this is our normal breathing pattern, this is abnormal breathing pattern. Beyond 50, this is our normal breathing pattern and this is abnormal breathing pattern. So it is a self-calibratory type of instrument. When a person is using it, first few minutes, it will detect that which type of breathing pattern is coming and which way the air flow should be controlled. The pressure of the air flow should be controlled according to the breathing pattern. As a result of developing this, we got this Best Student PG Thesis Award. Here is my student, MTech student Romanapur, and I also got award because of him as a guide in 2015 by the Institute of Mass Structures and Systems, which is DRDO lab at Kochi. Then the third one that I am going to show you, that is a smart wearable activity monitoring device. It is a cost-effective portable device that we are using these days, Mi Band or Google Fit, like that, where we have used MEM triaxial accelerometer to know the physical condition of an impaired person who is staying alone at a far end. Suppose a person having disease or persons staying alone at old age, sometimes it was difficult for them to carry the mobile phone always, but they can wear a wearable device to which we can monitor from other side that whether they are resting or walking or running, whatever they are doing, that we can easily monitor through our mobile phone. Similarly, working mothers like me, those whose children are in schools, creches. There also you can monitor what my child is doing, what kid is doing, done walking or sitting or sleeping or running like that. So as time is going on, the stay-alone persons, elderly stay-alone person is number of elderly stay-alone person increases worldwide. So now 1 in 3 adults of age 65 and older remain unattended. That serious trauma condition each year. That was, we actually got the information from who. And there are 2 types of ways to detection. One is mechanical pedometer, another is electronic pedometer. The innovativeness of our device or innovation of our device lies with, it is a stay-alone device. If in the marketly available device, that is in Google Pay, Mi Band or Google Fit, all are using mobile phone. You have to use your smartphone and the device. For processing, smartphone is compulsory. But here, if you are wearing this single band, it can process itself, no smartphone is required. So this is the spin prototype, X, Y, and Z axis. 3-axis accelerometer is there, MEMS accelerometer is there, that can actually detect 3 conditions of physical conditions like sleeping or resting, walking, and running. So this is the final device. And this is the thing we have measured. And here in X-axis, you can see Y-axis and Z-axis. This is for resting, this is for walking, and this is for running. And finally, we have compared our device with the marketly available device, that is Moto 360, Gen 1, Mio, Mi Band, Google Fit, and 4th one is ours. So if you see walking, error is less. For fast walking, again, error is moderate. For running, it is less. Rest, it is also within the limit. And overall error, it is again less. So it is a standalone device, low power consumption and microcontroller based, no external smartphone or PC is required. So it is energy efficient too, and from a child to elderly people can easily wear it. So we have introduced IoT in it. Again, a person having sugar or other thing, if doctor is asking him or her for physical fitness, they can wear this type of device and doctor can get the data on it. And final wearable device that I am going to show you is the smartphone. That is, we have developed a cost-effective self-stabilizing spoon for patients who are suffering in Parkinson's disease, having hand tremors, and facing difficult to have food by using, again, wearable MEMS triaxial accelerometer. So here you can see the person is facing difficulty while having food. Similarly, person is facing difficulty while serving food because of the hand tremors that occurs due to this type of Parkinson's disease. So this is the platform we have made where any type of spoon can be fitted. Till now, the existing solution is like this, means heavy weighted cutlery, spoon heavy weighted cutleries are given to them for the solution. But you can understand that a person having hand tremors to hold such a heavy weighted spoon or knife is again a challenge. And suppose there is an invitation, they have to carry their spoon or other things to go there to have food. So again, it is a problem. So we have actually developed this self-stabilizing handle They have to carry this portion only, and any spoon can be fitted so that the spoon can be washable. So this is our approach. So we are going to give a self-stabilized spoon handle. A MEMS accelerometer is connected with it. It is a C-axis accelerometer. So it can count both X, Y, and Z axis. Any standard spoon can be fitted on it. And when there is a hand trimmer, first few seconds, this MEMS accelerometer measures the hand tremors. Then it produces tremors opposite to the amplitude of that tremor so that it will be stabilized. So there is a servo motor that we are using here inside. Servo hinge, as you see, servo motor is there. So it counteracts the hand tremor direction. So this action keeps the spoon parallel to the horizon. This way, allowing the hand tremors to happen, but stopping them from reaching the spoon. So it stops. Hand tremors is there, but spoon will be not affected due to the hand tremors. So the food on the spoon will be stabilized. So this is the block diagram. So real-time implementation with different types of spoon. The spoon should be lightweight. A person carrying a willing to carry a lightweight spoon. As I told you, that this system consists of 3-axis MEMS accelerometer. So here we have used MPU 6050, the chip, accelerometer chip, which detects the direction and acceleration of due to the hand tremor. A low power microcontroller that we have used that detect the hand tremor, and it is also used to drive the servo motor. And it has been studied that a Parkinson's disease frequency range of hand tremor is in the range of 4 to 6 Hz. That varies person to person. So here you can see the SMT, and finally we are checking it. First few second hand tremors, it is collecting the data. Afterwards, it can find that we are moving our hand, but it remains still. So in spite of the hand tremors, now it stabilizes the spoon. So what are the attributes? You can wash the spoon. Google also developed one, but the circuitry, the stabilizing platform and the spoon are connected together, and they are very costly, but you cannot wash it. So here it is easy to wash. You cannot carry the whole thing together, and it is battery powered. So no shocking or something will happen. All software and hardware we are using open source, so anybody can develop it and can use it. So finally, we implemented it through IoT. So it is the patient having Parkinson's disease, and through which we can measure with medication whether it is deteriorating or frequencies are different components of frequencies, which frequencies are to major role, and what are the amplitudes, and everything we can measure. And finally, as a result, we got Rashtrapati Award, that is GHY Award in 2016 at Rashtrapati Bhavan. This is the joint award with my student Devjyoti Chaudhary. So thank you. Any questions? Any questions?
Hello.
Yes.
Thank you, ma'am, for your wonderful session.
Thank
To
you.
all the participants, if you have any questions, please ask or write on the chat box. Ma'am, there is a question. What regulatory and ethical hurdles do sensors face in healthcare applications?
Yes. One thing, if we remember that during COVID, we have purchased the O2 sensor. We don't know whether they are calibrated or not. We are purchasing so many sensors. In thermometers, we are purchasing some meters for measuring our blood pressure. So we don't know whether they are calibrated or not. But these are all non-invasive in nature. It are not harmful. We can use it outside our body. We cannot inject it inside our body. So this type of sensors you can use. And some ethical thing is there when you are going for testing. Then you have to take the ethical committee of that particular hospital should pass this. But till today in our country, there is no such rules that when this type of products are coming into the market, whether they are calibrated or not, people are checking. Even in the wearable devices like smart band and everything, that it can also measure our this breathing pattern or not breathing rate or something, pulse rate. So are they calibrated properly or not? We don't know, but they are purchasing. So wearable sensors or mark sensors, while people are producing, it is non-invasive in nature. So you can do it and you can check it with the other device, how calibrate it and check it that whether they are working properly or not. Are you satisfied with my answer?
Yes, ma'am.
Okay, any other queries?
Ma'am, there had been a comment given for your answer. Thank you so much, ma'am. It was amazing. An in-depth, clear, and fantastic session it was. Thank you so much for your time, energy, and in-depth discussion on the topic.
I've given you my mail ID, I think, at the beginning. So if you have
Ma'am, there is another question. Hearing aid battery with MEMS sensor, are there in market available?
Yes, nowadays you can see that the hearing aid, previously all hearing aids are actually visible. The person at young age, if they are having some hearing impaired or something, they are actually hesitating to wear it. Because by wearing hearing aid, everybody can identify that the person having some problem in hearing. But these days, this small hearing aid is coming, so it can be injected inside our ear hole or something. So it is now it is available in the market, but it is costly. Instead of what in the cost effective, now it's costly, but within few years, I think it will be very much costly. But our motto is to use that 500 or 600 rupees hearing aid that village people are wearing, mostly made by China. If you wear it, you can find it that there are lots of noises are there. So some people are saying that wearing the hearing aid, can't hear you properly. Lots of other sounds are coming. So that is the problem. Noise reduction is not good there. Microphone is not good. There we can use it. That's why I am implementing. Any other queries?
Thank you, ma'am, so much for your answer. Any more questions from the participants? Thank you, ma'am, for your wonderful session. We get to learn so much about the smart sensors that had been applied nowadays and your research work. So, ma'am, we would like to conclude the session. Yes, ma'am.
If anyone willing to work with me in my group, please write me or meet me if possible. Thank you so much for listening to me.
Okay, ma'am, sure.
Okay.
Thank you so much, ma'am. We would like to conclude the session here. Next, we would start the validatory session soon.
Did I leave?
Yes, ma'am, you can leave.
Okay, thank you.
Thank you, ma'am. Hello? Snehashish sir, are you present?
Yes, I am present.
Okay. As we come to the end of this faculty development program, I would like to extend my heartfelt gratitude to all the participants for their active engagement and enthusiasm throughout the sessions. This program has provided us with valuable insights, new perspectives, and practical tools that we can apply to enhance both our teaching and professional growth. I hope that the knowledge shared here will inspire all of us to continue learning, innovating, and making a positive impact in our respective fields. Thank you all for your time and staying with us over all the sessions. So now we would like to start the valedictory session. For that, we would like to invite Mr. Snehashish Banerjee, Secretary, Computer Society of India, Kolkata chapter. He is a senior scientist in TCS Innovation Lab. His field of research and interest is robotics. So now I would request sir to say a few words.
Yeah, thanks, Techno India Banipur for organizing this FDP session. And thanks also to Dr. Nag for inviting me and Dr. Odinarayan Khan sir for inviting me to this event. I represent Computer Society of India, Kolkata chapter. And in this occasion of the event, I would like to say a few things about CSI. So, as you might be knowing that among the societies that are active in this area, West Bengal, Region 2, CSI organizes the maximum number of conferences and online workshops, industry workshops. So I will request you to be part of the CSI fraternity, take advantage of the connects that you can get from the industry, government, and the academic partners that are engaged in CSI activities, and get involved in conferences like ICNSBT, EAIT, Human. These are the upcoming conferences that you can find by going to the website of csikolkata.org and clicking on the events link. So in future, we will like more such events happening in Techno India Manipur with collaboration with CSI. And I wish great success to the organizers as well as the attendees who are here for listening to the event, and eminent speakers and faculty development facilitators who has make this program happen with their tireless effort. Thank you.
Thank you, sir, so much for sharing your some valuable words with us. Next, I would like to invite Professor Harinarayan Khan to share a few words about our FDP. But before that, I would give a short introduction of Dr. Harinarayan Khan, who is currently working as the head and associate professor in the Department of Computer Science and Engineering in Techno Engineering College, Banipur, West Bengal, India, under Maulana Abdul Kalam Azad University of Technology, Makaut, Kolkata, India. He received his PhD and Masters of Technology in Computer Science of Engineering from Jadavpur University and BTech from Makaut, which was formerly known as WBUT. His research interests include cryptography, network security, information sharing, steganography, watermarking. Dr. Harinaran Khan had served as one of the organizing chairs for our faculty development program organized by TCB, Techno Engineering College, Banipur, in association with CSI. So, sir, please take over the session to say a few words.
Hello, hello, hello. Am I audible? Am I audible? Hello. Am I audible? Okay.
Yes, sir, you are audible.
Yes, thank you. Very good afternoon to all of you. Honorable Chief Patron, Professor Dr. Gautam Roy Chaudhary, sir. Honorable Chief Patron, Professor Dr. Manushi Roy Chaudhary, ma'am. Respected Principal, Professor Dr. Malay Kumar Chandra, sir. Respected Advisory Committee, Mr. A.K. Roy, sir, and Mr. Pradip Padi. Respected conveners, Dr. Indrajit Sadhukan and Dr. Aniruddha Nag, sir. Honorable Chief Guest, Professor Dr. Atul Chaudhary, sir. Respected guest, Secretary, Computer Society of India, Kolkata chapter, Mr. Snehashish Banerjee. All the faculty members and staff of Techno Engineering College, Banipur. And dear students, dear participants, as we gather here for the valedictory session for this faculty development program on computational tools in engineering and research, issues and challenges, I feel privileged to stand before you, reflecting on the journey we have undertaken over the past few days. This program has an enriching experience where we not only explored the latest computational tools that are shaping the future of engineering and research, but also engaged deeply with the challenges and opportunities those tools bring to our academic and professional lives. We have had a privilege of learning from expert speakers, engaging in stimulating discussions, and participating in hands-on sessions that have broadened our understanding and rapidly evolving landscape of computational methods. Our discussions have touched upon critical areas where it was the importance of integrating computational tools in curriculum design, overcoming the challenges of data management, and the need to stay updated with cutting edge software and programming techniques. More importantly, we have explored how this tool can be harnessed effectively to solve real-life engineering problems and contribute to innovative research that can transform industry and society. It is clear that as educators and researchers, we must continuously adapt to the advancing technological frontiers. The tools we have discussed here are not just asset for individual growth, but are transformative instruments that can propel our institute and students toward greater success. However, with this power comes the responsibility to not only master these tools, but to impart this knowledge to the next generation of engineering and researchers, ensuring they are equipped to navigate the complexity of the future. As we close this program, I encourage each one of you to take what you have learned here, share it with your colleagues, students, and continue to build on the foundation we have laid. The challenges may be many, but the potential for impact is boundless. And it is in our hands to lead by example. I would like to take this opportunity to extend my heartfelt thanks to our distinguished speakers and resource persons for their invaluable contribution, to the organizing committee for this dedication in making this program a success, and to all of you, the participants, for your active engagement and enthusiasm. Together, we have made this program a meaningful learning experience, and I am confident that the knowledge gained here will have a lasting impact on our professional lives and broader academic community. Thank you. I wish you all the best as you return to your institute, ready to make a difference through the power of computational tools. Thank you. Thank you very much.
স্যার এটা নিন, হবে না, হবে না, ইকো হবে, এটা নিন।
Hello.
For our final portion of the valedictory session, I would like to call on stage one of the conveners of our 5-day faculty development program, Dr. Indrajit Sadhukan. He is Assistant Professor of Physics at Techno Engineering College, Banipur. Dr. Sadhukan obtained his graduation, post-graduation, as well as his PhD from Jadavpur University. He is a recipient of National Scholarship during his higher secondary examination, and also a recipient of Young Scientist Award from Department of Science and Technology, Government of India. He has many research papers in international and national journal and conferences. He is one of the key figures behind this FDP. So to deliver the vote of thanks, now I would like to call sir on stage.
Hello, am I audible?
Yes, sir, you are.
It is with immense pleasure and gratitude that I stand before you today to deliver the vote of thanks on behalf of the organizing committee. The Faculty Development Program on Computational Tools on Engineering and Research, Issues and Challenges has been an enriching and insightful experience, and I feel honored to extend our heartfelt appreciation to all those who have made this event successful. First and foremost, I would like to express our sincere gratitude to our chief guest, Professor Dr. Atal Choudhury, and the distinguished speakers, Professor Dr. Shubhobroto Roy Choudhury, Dr. Parijat Chakraborty, Dr. Soumen Mukherjee, Dr. Piyush Datta, Dr. Nishant, Dr. Ajit Kumar, Dr. Soumojit Goswami, Dr. Arindam Sarkar, Dr. Seshang, Dr. Abhijaan Bhattacharya, and Professor Madhurima Chattopadhyay for taking time from their busy schedules to share their knowledge and experience with us. Your in-depth presentations on the various computational tools and their applications in engineering research have been truly enlightening. The discussions on the current issues, challenges, as well as the future directions in the field have provided us with valuable insights that will undoubtedly enhance our teaching and research. We are also deeply thankful to the organizing committee for their tireless efforts in ensuring the smooth conduct of the program. Your hard work and dedication have made this event a success. A special word of thanks goes to all the participants who have shown their keen interest and active involvement throughout the sessions. Your enthusiasm and eagerness to learn have added tremendous value to this program. Lastly, we must extend our gratitude to the management and administration and technical team, especially Mr. Bijon Borai, Chandrasekhar Bhattacharya, and our host, Mr. Shubhankar Bhattacharya, for their continued support in organizing such programs, and to everyone involved in making this event a resounding success. As we conclude, we hope that the knowledge gained from this program will empower all of us to adopt and integrate the latest computational tools in our respective fields and continue to explore new avenues for research and innovation. Thank you all once again, and we look forward to meeting you at future events. Thank you.
Thank you, Dr. Shadu Khan, for your vote of thanks. We will now conclude our session. There will be a final evaluation session, details of which will be provided in the official WhatsApp group. So for now, I am Shubhangan Bosu, Professor of Basic Science Department, signing off on behalf of Techno Engineering College, Banipur. Thank you. Have a nice day.